Here we go. So, before we get started, this is an interactive presentation, so please either go to t.mp/PyTX 2026, or you can click on the top link in the PyTexas.org links, and it will take you to a instruct environment. This environment will take a little bit of time to load, so as long as you click in and you get it going, I will also run this on my own machine, so that way we can do it together, which is going to be fun for me to try to figure out how to do this and look sideways at the same time. So t.mp/PyTX 2026. And this will open up instruct. We click start. And then this is going to take a couple minutes while it's provisioning. We'll begin the talk. So I will give you about 30 seconds to keep doing that, or go to the PyTexas links site, and we can go from there. But yeah, this will be an interactive presentation. So I have to put the hat on, because I'm no longer PyTexas Mason, I am now Temporal Mason. So my name is Mason Egger. I am a senior solutions architect at Temporal. I help customers implement durable execution solutions on the commercial side, and prior to that, I did a lot of work on their education, their documentation. So if you've ever taken any of the Temporal courses or do any of that nature, you will see me doing a lot of it. So today, we're going to talk about events and event-driven architectures, and I'm going to tell you right now that events are the wrong abstraction. So who knows what this is? Who knows what this picture is? Any idea? Orbits, yes. So this is a map of our solar system, but it's a geocentric projection. So this is how the solar system looks if you map the path of the celestial objects around the Earth instead of around the sun, okay? It's very beautiful. It reminds me a lot of those spirograph tools we might have all played with in kindergarten. Millennials will know these really well. But it's a really cool, beautiful representation, and this is accurate. This is a totally accurate diagram. It's beautiful, but it's complex. Then in the 16th century, we got Copernicus, this wonderful, person, who decided to put the sun at the center of our solar system. And then suddenly the ecosystem got a lot simpler. Things made a lot more sense to us. Now, for all those that are like, they're not circles, they're ellipticals, I don't care. We're not going that deep into it. But essentially, this actually allowed us to start thinking about things differently. We discovered things about nature that we had not learned before. This actually inspired the law of gravity and the way that we worked on things. All sorts of new scientific discoveries were made, not because anything about our known universe changed, but because we looked at it through a different lens. We reoriented ourselves around what we put in the center. It's important to note that these two diagrams are not incorrect. They are both accurate. They're both useful, but they're not always useful for the same things. So for example, if we want to do like moon trajectory with the Artemis 2 and stuff, we probably do need a spirographic representation of it. Because if I need to be able to calculate how to send those astronauts and hopefully get them back. If we're trying to do things with intercelestial objects, then we probably need to be putting the moon at the sun at the center of our ecosystem. So you may be wondering why I'm talking about this. We're all in here, we're all building software. We are ensuring that our software is available and scalable to others. And this is a challenging thing to do. Anyone who's ever had to actually put something into production, making sure that it is available is a difficult thing to do. And then now, everything is a distributed system. Every application on Earth is a distributed system now. How many applications do you interact with on a day-to-day basis that do never touch the internet? Not that many. Go back to the 90s. For those of us that were alive back then. How many applications did we touch back then that never touched the internet? Quite a few. We used to put in the floppy disks and install it, never touched the internet. So once we added the internet into our architecture, everything became a distributed system, and then we did something even more fun, which is we broke up our beautiful, wonderfully working monoliths and created microservices. So even if we didn't need to make stuff talk across the internet, we did it because it was fun. I'm not going to get into that, but this will be a mildly spicy talk. We have patterns for solving all these problems, and one of the main patterns we have is event-driven architecture. So, what is event-driven architecture? It is, by definition, a software design pattern where the components communicate by producing and consuming events, allowing for the loose coupling and asynchronous processing where systems react to state changes or occurrences rather than direct method calls. So, that's a pretty academic version of it, but let's look at like a real-life example. So let's say I have a payments architecture, okay? And a person makes a payment, which is then sent to my payment ingestion service. This service initiates a payment for the users and validates basic payment structure. The payment ingestion service then publishes the payment as an event on said message bus. Now, if that publish doesn't work, well, then we'll need to retry until it does, because we want to make sure that that payment goes through. And if that payment failed validation, well, now we need a dead letter queue that we need to be always constantly checking for stuck payments. And then the payment processing service is then subscribed to said message bus and sees the event. So it processes the payment typically via a temporary auth. Maybe if you're getting lunch and you want to leave a tip later. Then the payment processing service writes this to the database, updating it later in case someone does say leave a tip. But I hope you don't lose that update, because then it all drops off and now you don't have a database right and transaction. And there turns out there is such thing as a free lunch. And if then at the end of the day, we send stuff to a daily batch aggregation job and accumulate all the payment groups from that, and then the aggregated data is sent to a clearing service, and finally we write back to our payments accumulation database. So this is a very simplistic version of payment accumulation. And some of you might be looking at that going, yeah, it's a darn good architecture, ship it. Like, that seems fault tolerant, seems resilient, seems awesome. But I ask you this, do we have the right thing at the center? What is at the center of our logic here? Is it our business logic, or is it our fail-safe and all of our infrastructure to keep us from crashing? In this ecosystem, events were what we've made the center of our universe. So we have the wrong thing in the center. We built our applications with events at the dead center of it instead of our core business logic. If you look at that diagram that I had, there were more moving parts that dealt with events than there was actual business logic that made the company money. There will be more infrastructure there to support that than there will be the business logic that makes the company money. In a past life, I was an SRE. I've seen dead simple logic and topple enterprises because of mismanaged queues. So if you want to know about my horror stories, find me at lunch. So there are some issues with this approach. How much time do you have? I only have a short amount of time, and we could go on this for hours. So let's just talk about a few of them that bug me about event-driven architectures. There's no APIs in an event-driven architecture. We sacrifice clear, well-defined APIs when we have adopted events. We don't have documentation or structure in our events, leading us to ambiguity about which events each service consumes and produces. And yes, there is an async API spec, but that focuses on the formatting of the messages. It's not about an API, just about what was produced by the thing. And we all know that developers are great at documentation, right? So you're all going to document every single aspect of your event-driven architecture so everybody knows what you're always doing, right? Wrong. I worked in documentation for years. I'm not worried about AI taking my job. You're too lazy to even write the prompt that says, write the docs. I'm fine. I'm fine. Scattered logic. This is the other thing. Business logic becomes fragmented and spread across so many different services. Instead of having a bug and saying, let me look at what happened, now I have to open multiple files. I have to grep across an entire code base by event name. And in some worst case scenarios, the only way for me to reproduce the bug is to run the darn thing again. There's no way to find it other than that. We have built how many APM companies have spun up because we could not be able to trace our events through a call stack? This happens all the time. Every service is now an ad hoc state machine. Woo! Every CS major on earth is cheering for this because they all love their state machines until you get paged for one. And the minute you get paged for a state machine breaking, you never want to see a state machine again. Okay? The services all have a local database. You can produce and consume messages. In many cases, there are not transactions between publishing the message and updating your state. So hope you don't lose it again. Hope the network's super reliable. Race conditions. Now we have everyone's favorite thing to debug at 2 o'clock in the morning when your pager duty goes off. It's race conditions. It's the bug that scurries away and doesn't make itself known, and then you have to find it again later. Now you have extra logic. Or what you can do is what a lot of insightful companies do is you can just always push this off onto your customer support. Customer support will handle this. They'll just reset the system. It's not a great way of running a business. I heard someone moan. So obviously there was a part of your life where that was the thing, and I feel sorry. All of this to say, this all actually leads to a very tightly coupled architecture. Now, before you throw the tomatoes, I understand that we are told in our books that event-driven architectures are loosely coupled. It's not right, and it irritates me. They are when we use them because the systems go down and other systems can keep functioning, and this is awesome runtime characteristics. So people assume that they are loosely coupled at runtime, but they are also loosely coupled at design time, and that is completely not true. So imagine this scenario. You come in and someone says, you're doing a code review with a junior engineer, and they come in and say, I refactored our service code and everything is way more loosely coupled. And you go, wow, that's amazing, how did you do it? And they say, I made all local variables global variables. And you're like, oh my God, why did you do that? It's like, well, it's easy. You can just add new code here, and the old code doesn't have to worry about it. We can just add new things in, everybody consume it. And you all sounded like that was preposterous. That is exactly what event-driven architecture does. We just publish stuff into the ether and pray nobody ever changes it. We can just reform we can just read from this event, and it just becomes a problem. So what this does, this leads to an engineering culture of fear of changing things. You get really worried about changing the events that you have published because you have no idea who downstream is consuming them, because they're not telling you. You have no way of noticing that. And then when you turn it off, you cause us to have one outage. Ask me how I know. Don't ask. We wind up with these Rube Goldberg, Dr. Seuss machines where you're flying down through the road, honking the horn, praying that the God of Thunder doesn't strike you out of the thing. And what ends up happening is instead of building a refactoring, now you have event v2. And now we have all the new ones. And that'll last you until it's time for you to move on to your next job, and then the next engineer has to come up and clean up your mess. So we've created this kind of ecosystem around it. So I ask ourselves, let's put the right thing at the center, let's take a step back and try to find a different way of doing this. And I think that the center of this is actually durable execution. So what is durable execution? It is basically what we call crash-proof execution. It enables the developer to write reliable software with less effort. It allows them to focus on what applications should achieve instead of trying to anticipate and mitigate every single way that something could possibly go wrong. This in turn accelerates development. Failures are inevitable. Durable execution makes failures inconsequential. You don't have to worry about them anymore. So what are some of the characteristics of it? Well, it automatically preserves application state. It virtualizes your execution. It's not limited by time, and it's completely hardware agnostic. So let's actually see this in action. Let's go. Now this is where I'm going to go, and you can follow along in your instruct environment. Hopefully it's done booting. If anybody has any problems, let me know, because this is a new tool, new toy for me. So if it's being weird, I did not hit start at the beginning, so now we get to wait a whole another 2 minutes. We're skipping sample 1, because I do not have 2 minutes to wait on that. Wow, okay. Make sure you hit start before yours. So, any questions so far? No? Go? What? How do I know what? Oh, I cannot hear you over that. Catch me later, Bernat. I have a feeling that's heckling, not a question. But that's fine. So let's actually look at how durable execution virtualizes visualization, okay? Say you have an application process and you start and you have process 1. So we run our first function call within process 1, it completes successfully, it's fine, then we go to process 2, but let's say that process 3 crashes, okay? Normally, what would happen if you were running, say, like a loop that was counting from 1 to 10, and you crashed the loop in the middle of it, say at step 5? What would happen? If you start the app program again, what number would it start at again? Just shout it out. 1, starts over. Applications don't maintain state, not with durable execution. So in durable execution, we get to this failure. The process itself is cloned. The original 2 events are replayed. We have maintained the state, so we don't have to re-execute the execution. And now process C runs totally fine, but oh no, process D fails. Oh, well, it doesn't matter. We're just going to replay the entire event structure again. We're going to build out A, B, and C, and now D works. So this is done seamlessly under the hood. Developers never aware that this is actually happening in their code base. And what it does, it creates this kind of this representation between the physical representation and the logical representation. So what happens is with this developer experience, what the developer experience is, more importantly, what the customer experience is complete seamless execution, maybe a small amount of time between where these things crash and they respun up, but really these things replay in microseconds or milliseconds, so it's not a really big problem. The developer experience and the user experience completely awesome with that. So let's go back and see if I waited the appropriate amount of time this time. We did, so we can actually do this in reverse. Okay, so this is the normal set of code for my very first example application, and this is a durable execution example using temporal. In a normal durable execution example, what I can do, let's see if I can remember. Nope. There we go. I start running my counter, and if I kill it, nope. If we type the right command, that's it, okay. I remap my keyboard, and sometimes I never have to use Control-C, so come on. We'll just recopy the whole thing. We begin running it, and if we kill it, okay, fine. And if we start it again, it starts at the beginning again, like we expect. But with durable execution, what I can do, it is just not going to like me today. It's fine. This is because I'm not good at typing. Okay? And then we run, and just run worker, Python, worker.py. So now if I begin running it, and I kill it, and I restart it, we will have maintained application state as it's replaying and rebuilding, and the application continues on normally. No lost state, nothing was lost here. The code looks a little bit different, obviously, because we have to save state in a function. I had to have like a little mini function call for this. But yeah, this is how this works. So now, if you're really interested, we can play the next one, which is way more fun. Do not take 2 minutes. We are going to have a hard day if you decide to take 2 minutes. There we go, start. So now we're gonna run Wordle. This is a durable version of Wordle. So if I come over here and I copy this, and I run it in this ecosystem, we'll have our worker running, and then we'll have our web server running. And then we come here and we should get Wordle. Okay, so now we just do radio. That's my normal, typical daily one. Okay, so now we could go through and we could send another thing, but what happens if we kill the application while we're doing this? So let's just kill the whole worker. And I come back in, and so I'm not gonna even try. So, okay, I hit enter, nothing happened. I come back over, I rerun my worker. Wordle worked, just continued on. We don't lose state of our application. There's no database calls that you're ever performing in this. All you're doing is writing function calls. You get this out of the box. Now, I'm gonna cheat because I wanna know what the actual answer is. So, because of the way that temporal works, I can just go and look at the event history and see what it actually decided it wanted to select. The word is yield. Every single input and output to every application is stored by default inside of this web UI that you have access to, that you can use. So now if we just go back over here and we type yield, we have the word. And we have a completed workflow with durable execution. And I will make this code available after the fact so you can look through it. But at the end of the day, you get all of this observability. Like, how many people are by default have this kind of observability in their code base, like without having to wire up Datadog or anything? Probably not, right? So durable execution, because of the way that it works, provides all of this event history, all of this event sourcing. It persists over all failures and things like that. So when we look at our architecture diagram, now a person makes a payment. It goes to a payment ingestion workflow. At the end of the day, it writes everything out to a payment accumulation database, and then we send everything to a clearing service at the end of the day on a schedule. Our architecture is vastly simplified. There's no plumbing, and there's less places for it to break. So, and I would say it's a lot simpler. You want to know a fun little secret? It's all still events under the hood. It is. This is still event-driven architecture. But what's the difference here? We've abstracted the complexities outside of the platform layer and into the software layer. Okay? This is actually a very common thing that we do in software engineering, is that how many of you still go decide, I'm gonna write program today, and you pull out your x86 architecture handbook and you're like, we're gonna write some assembly. No, some people might, yeah, for fun. You don't do that anymore. We've abstracted it away from the hardware and into the software layer. So this is the exact same thing, is we've abstracted event-driven architecture, all of these things, queuing mechanisms, timers, retries, all of that, out of the layer to where you never have to really worry about it, and by default, your application gets it. And you get a cute little unicorn that goes across the screen at the end. Whee! So, what can durable execution be used for? Everything. Like, it's a really fun question that always makes it fun for me whenever I have to talk to people at PyCon about it. But I'm being serious. It really can be used for everything. Here's what you should say. Do you want your software to not fail? Good. Then durable execution is for you. Hooray. Easy. Here's a couple of lists of things that it is used for based off the customers that I've worked with. All different types of processes, like money management, process payment, booking, logistics, everything you can think of. Lifecycle support, inventory management, CI/CD, multi-version versioning, customer lifecycle, infrastructure services, provisioning, software updates, ETL, a whole bunch of AI use cases. If you type something into OpenAI today, it goes through temporal. So, like, there's a lot of use cases for this. And the good thing is, we're open source. It's MIT licensed. You never have to pay me a penny. Like, it's great. Woo! We have SDKs in 7 different programming languages, okay? This is the part that I was hoping Peter would like with my little flips. So, and we'll have a Rust one soon. So, like, that'll be the end of that. There's some community ones. Some poor soul decided to write a Haskell one. Good for them. But yeah, so that's what temporal does in durable execution. How would you get started? You can go to the docs. You can go to the Learn site. You can go to GitHub. Just play with it. Download. It's a single binary to build and run on your machine. There are parts of the PyTexas conference that are running on top of a self-hosted single binary temporal cluster right now. That just makes sure that whenever our GitHub, our webhooks or something fail, it automatically does the retries for us. It makes my life so much easier. And if you want to conference more, you can come to Replay in San Francisco 2 weeks from now. And if you would like, I have a discount code. It's called Mason, so it should be really easy to remember. But you can come if you're for some reason you're in San Francisco or you feel like making the trip out and you want to come to our 5th conference, and which will be the largest one. You can definitely come out and join us there. Are there any questions or anything you would like me to go over? I'm done. Woo.
Can temporal interoperate with async IO or AIO HTTP?
Yeah, it's built on top of that. So if you remember, if you were here last year, Chad Reitz gave a talk on how Temporal built a custom async event IO loop for Temporal. So it interacts with everything. The great thing about Temporal is that you get to keep all of your tooling. It's just SDKs. It's pip install Temporal, okay? So whatever tooling you're already using, whatever you want to use, your favorite package manager, your favorite libraries, it just interacts with that. So it works with async IO out of the box. There's both a sync and an async version because Python developers are notoriously bad about writing async code and not blocking the event loop. This will be the thesis of my life. So yeah, but it works with darn near everything. And the one thing I didn't mention is it all speaks gRPC under the hood, so it's natively polyglot. Do you have a workflow that's written in Java, but you want to be able to call one function in Python, and you're like, damn, I know I have to build all this stuff. No, just call the function. It goes through, natively works without under the hood.
I will give you more. And
okay.
There's a pile, so we'll take them.
How are the bindings generated? Is that all from one skeleton?
The bindings for like the API,
The language APIs.
Those are actually handcrafted with love. So it's not an open API spec. That's a great question. So it's one of the things that I like talking about, which is all of our APIs are actually built, or all of our SDKs are built by people who sit and study the programming language. So Chad, if anyone met Chad last year, he was the author of the Python SDK. He never wrote a line of Python in the a day before in his life before he started working on the Python SDK. It is the most Pythonic SDK I've ever seen in my life. He sat down, he dove into the language. We don't want to just, like, you've used bad APIs, where you feels like you've bolted a C API on top of something and it's returning integers in Python and you're like, what is this, 1993? But no, these are all built by hand and they have their own, so they have, it's fun is that they have different SDKs can interact with the language, their interactive languages different ways because we dove so deep into the core functions. The Python SDK uses async IO natively out of the hood. It uses decorators to tell whenever you're doing, like, this is a function, this is an activity, this is a workflow. It uses data classes for serialization. It uses all of that stuff. But if you use something like Ruby, Ruby uses class-based inheritance. So it's doing all of that. So it's really deep in the programming language.